Hi, today I will review about the PN junction. So let's start. First, let's talk about the IV curve of the PN junction. If we put the 4 BS to the junction, and then the current will flow like this, like exponentially. So if when the 4 BS put to the PN junction, the current will be flow like that, and then the left side of the zero is the reverse bias part. So if we put the reverse bias to the PN junction, the current will flow very small in this part. So we should know about the characteristic of the current when the specific bias put to the PN junction. So we reviewed about the IV curve first. And then let's talk about the electron and holes concentration of two types of N-type, each N-type and P-type. So first, let's look about the N-type. N-type, it has more electron than P-type semiconductors, so there are a lot of electrons in here. So electrons are more than holes, so the concentration of between two is very big, a big difference of between two. So we should know about the characteristic of N-type, that electron concentration is very bigger than holes concentration. So we should know about that characteristic. And let's look about the P-type. P-type has more holes than N-type. So there are, I just drew very little, but actually it looks like N-type's electron concentrations. So there are many holes in the P-types. So we should know about the difference of two types of semiconductors. Because of those concentrations, the Fermi level is changed by that concentrations. So in P-type, the Fermi level is very lower than N-type, but it is very near at the vacuum level. But however, in the N-type, the Fermi level is near the conduction band level. So we should know about this difference. And then let's talk about the energy band diagram. I just drew the vacuum energy level and conduction band level and valence band level. Actually, this red line is the intrinsic Fermi level of this PN junction, but this purple line is the intrinsic Fermi level of this PN junction. However, this red line is the Fermi level when this PN junction is on thermal equilibrium. So if this line, the Fermi level line, is flat, we should know that PN junctions temperature, or yes, the PN junction has a thermal equilibrium state. So yes, we just talk about this red line based on this red line. So because of this red line, we can know this left part is the N-type and this right part is P-type, because the Fermi level affected the types of semiconductors. So yes, actually, before we talk about the Fermi level of N-type and P-type, the Fermi level of N-type is near the conduction band level. However, the Fermi level of P-type is near the p-type valence band. So based on that theory, we can know about the types of two parts. So yes, and then the middle reason is the depletion reason. Actually, we can also call this reason space charge reason, because there are only space charges are located. So yes, and then there are no electron moves or holes moves, so we can call this reason depletion reason too. Yes, we can know many things about this energy band level. And then let's talk about this built-in potential. Actually, we should know about the junction potential of semiconductor, because we should calculate something based on this junction potential. So we should calculate the junction potential, but actually every semiconductors have their own built-in potential when they be made. So this is this green line. Green line is the original built-in potential about the semiconductor. So actually we can calculate the junction potential based on the built-in potential and applied potential. After we applied some voltage to the PN junction, we should know how much voltage put to the PN junction. So if we want to know about the junction potential of PN junction, we should minus built-in potential minus applied potential will be the junction potential of the semiconductor. So we should know the junction potential based on this equation. So we should know about this equation too. Then let's talk about the tunneling current. Actually, if we apply very high voltage or very low voltage, this curve will be different than before, because this built-in potential equals junction potential is affected by the applied voltage. So if we apply so high voltage, this barrier will be very thinner than before, because yes, we should apply a lot of voltage. So if this barrier is very thinner than before, the current can jump to the right side or left side easily, because the barrier is very thin. So we call that situation tunneling current. So after the electron tunneling to the other side, when electron moves to other side, that makes current. So we called it tunneling current. Yes, so this is a simple graph of tunneling current, and this is the IV curve of that tunneling current. So yes, this part, there are very small current will be flow, but however there will be very low yes, like current flow will like that. So yes, we actually sometimes use this tunneling current, and actually we should know about this tunneling current and then make this semiconductor more effective than other device. So yes, and then let's talk about the current of PN junction. So actually we learned about the N-type and P-type before, so we should know about the concentrations about those two types. So yes, actually N-type, there are a lot of electrons in here. However, there are smaller holes in here. So that concentration will be gonna be smaller when it goes to the left. Then because of the difference of the concentration, that makes diffusion current. This is very important current. And then the holes is getting lower concentration, so also it makes drift current too. So yes, current is equal to diffusion current plus drift current. So actually on the right side it is equally happened with the left side. So yes, they also flows drift current and diffusion current on the p-type. So we should know the current flow and why and how those currents flow like that. Yes, because of concentrations. And let's talk about Schottky diode. Lastly, Schottky diode is made by metal and semiconductor. So this part is metal, and yes, this energy band will be semiconductor. So actually metal has a lot of free electrons and also has equipotential. So if the electrons or holes meet those free electrons, they combine easily. So actually every materials have their own electron affinity. So because of that, that graph, that energy band level will be drawn like this, like curve. Yes, it is a little bit different with other original energy band, but yes, Schottky diode is a little bit special, I think. So we can draw like that. And then yes, that Schottky diode has a depletion region in the middle. So yes, and then actually this Fermi level is more higher when before they meet. However, after they meet together, after they combine together metal and semiconductor, that Fermi level will be lower than before, and then this graph will curve like that. So this is the main important thing of this Schottky diode. And then if we apply a high voltage to this Schottky diode, that energy level band graph will be, the curve will be lower than now. However, if we put a big reverse bias, that Schottky barrier curve will be more curving, like more lower like this. So yes, it will change like that energy level which we learned before, like PN junction. So yes, it will also work like that. So today we talked about the PN junction and Schottky diode. Thank you for watching my video. Bye.